Hello everyone. Today I'm going to talk about fundamentals of one-dimensional water flow in soil. Soils are permeable because of the presence of interconnected voids through which water can flow from points of high energy to points of low energy. The study of the flow of water through permeable soil is important in geotechnical engineering. It is vital to estimate the quantity of underground seepage under various hydraulic conditions, to investigate problems including the pumping of water for underground construction, to make stability analysis of earth dams and earth retaining structures that are subjected to seepage forces. One of the important physical parameters of a soil that governs the rate of seepage through it is known as the coefficient of permeability. The question is, what produces the flow of water through soils? Below the water table, the pore water may be percolating through the soil under hydraulic gradient. According to Bernoulli's theorem, the total height at a point in water under motion can be presented by the summation of pressure, velocity, and elevation heights, or as formulated here. In this equation, H sub P is equal to pore pressure divided by unit weight of water, and H sub V, which is the velocity had, is equal to V squared divided by 2 times G. V is the velocity of water seeping through soil mass, and G is the acceleration of gravity. H sub E is the vertical distance of a given point above or below a datum plane. If Bernoulli's equation is applied to the flow of water through a soil mass, the velocity hat can be ignored because the drainage velocity is very small. In the figure above, pressure, elevation, and total heights for the flow of water through soil mass are illustrated. The levels to which water rises in the piezometer tubes installed at point A and B are known as the piezometric levels. The pressure head at a point is the height of the vertical column of water in the piezometer installed at that point. Referring to the figure, the head loss between 2 points A and B can be given by this equation. The head loss can be expressed in a non-dimensional form as delta H over L, where I is the hydraulic gradient, L is the distance between points A and B, which is the length of flow over which the loss of head took place. Darcy recommended that there is a simple relation between the discharge velocity and the hydraulic gradient. Let us see what it is. V is equal to K times I, where V is the discharge velocity as defined earlier, and K is the coefficient of permeability. Nevertheless, the actual velocity of water seeping through the voids of soil is greater than the discharge velocity and can be given by dividing the discharge velocity by the porosity of soil as illustrated here. Therefore, the rate of flow can be expressed by A times V or A sub V times V sub S. Or it can also be expressed in terms of A times K times I. I is the hydraulic gradient. In these equations, A is the cross-sectional area of soil and AV is the area of void in the cross-sectional area of soil perpendicular to the direction of flow. Darcy's law is valid as long as the flow of water through soil is laminar. The permeability of soils depends on several factors, such as soil type, particle size distribution, pore fluid properties, pore size distribution, homogeneity, layering and fissuring, and entrapped gases. Cohesionless soils have higher permeability than cohesive ones. Poor graded soils have higher permeability than well-graded soils. When the viscosity of pore fluids in a given soil increases, then the permeability decreases. The greater the interconnected voids, the higher the permeability. Water tends to seep quickly through loose layers, fissures, and along the interface of layered soils. Entrapped gases tend to reduce the permeability. Even soil, even soils that are under groundwater may still have some entrapped gases. The hydraulic conductivity of soils is characterized by the coefficient of permeability. Typical ranges of coefficient of permeability for different types of soil are presented in the table here. Notice that as the particle sizes decrease, the permeability, in other words, the hydraulic conductivity of soil decreases too. As the gravels have the highest permeability of 10 to the minus first power, clay soils have the lowest permeability of 10 to the minus ninth power. Is it good or bad for a soil to have a very low coefficient of permeability? In many cases, soils with very low permeability are clays that include smectite. As water seeps through soil, the process of consolidation, in other words, removal of water from soil, takes much longer than for soils with high permeability, such as sand and gravel. Nevertheless, there are some positive aspects too. Soils with very low permeability are employed in dam construction to lessen the flow of water through them and as liners to hold municipal waste as they prevent toxic leachates from contaminating groundwater. How is the permeability of soil determined then? Well, it can be worked out in the laboratory from either constant head or falling head tests, depending on soil type. typical setup of constant head permeability test is shown in the figure here. The test is employed to determine the coefficients of permeability of coarse-grained soils such as gravels and sands. In this arrangement, water flows through the soil under a head which is kept constant by means of overflow arrangement. Excess water is drained through this pipe to keep the water level in the tank constant. The head loss between 2 points along the soil sample, as shown in the figure, is measured by means of standpipes. Provided that the constant flow rate is established, water gathered in a graduated flask for a known duration may be given as A times V times T. In other words, A times K times I times T. In this equation, Q is the volume of water gathered in a graduated flask, and A is the cross-sectional area of the soil sample, and T is the duration of water gathered in the flask. Since hydraulic gradient is the ratio between delta H over L, if this expression is involved in the above equation and the equation is rearranged in terms of K, we get this equation as written here, which is needed to calculate the permeability of soils subjected to constant head permeability test. In the figure here, you see a typical arrangement of the falling head permeability test. This test is employed to work out the permeability of fine-grained soils such as silts and clays. The test is carried out by filling the standpipe with de-aired water while the valve is closed, and then the valve is opened. Meanwhile, a stop clock is started. During the test, the water in the standpipe drops from a height of H sub 1 to a final height of H sub 2. Let H be the height of water at some time t. Take a small time interval into consideration and let the change in the level of H during this time be dH. It is negative because it represents a drop in elevation. The velocity in the tube can be given as minus dH over dt, and the inflow of water to the soil can also be given as minus A times dH over dt. Now, regarding Darcy's law, to get the outflow, Q out can be written as A times K times H over L. The continuity hypothesis necessitates that inflow of water is equal to outflow of water. Therefore, minus A times dH over dt is equal to A times K times H over L. Separating the variables and integrating between the suitable limits as given here, the above equation leads to this formula. which is used to calculate the permeability of fine-grained soils subjected to falling head permeability test. So far, we have considered the flow through homogeneous soils. In fact, water flows through several soil layers. The question is, how can the flow of water be estimated in that case? Well, in such cases, an average or equivalent permeability representing the whole soil mass is obtained from the permeability of each layer. Let us consider a soil mass made up of 3 different layers. Each has different properties in terms of permeability and thickness. And the soil mass is subjected to horizontal flow. For flow that is horizontal, head loss for each layer will be the same. So will be the hydraulic gradient. For each layer, the rate of flow of water can be obtained from Darcy's approach. For example, for the first layer, the rate of flow of water is equal A times K times I. A is the cross-sectional area of the first layer, perpendicular to the flow of water. K is its permeability, and I is the hydraulic gradient. For each layer, the rate of flow of water can be figured out in a similar way. The total flow of water is the summation of the rate of flow of water for each layer. Now then, if we substitute and rearrange in terms of K value, we get the equation given here, which is for the estimation of an average or equivalent permeability representing the whole soil mass subjected to flow parallel to soil layers. For flow vertical to soil layers, the rate of flow of water for each layer will be the same. However, the head loss as well as the hydraulic gradient will be different. In that case, the rate of flow of water passing through soil mass can be given by A times K times I. A sub V is the cross-sectional area of soil mass perpendicular to the flow of water. K sub V is the average permeability of the soil under consideration, and I sub V is the total hydraulic gradient, because the head loss for each layer is different as shown in the figure. If we express head loss in the form given here for each layer, and if we substitute and rearrange in terms of K value, we get the average permeability of soil mass for the case of flow vertical to soil layers. Now, the equivalent permeability for both flow can be estimated by the equation given here. Here it is. A practical example. A trench of 1 meter length is to be excavated for a gas pipeline near a temporary water-bearing canal. The average vertical and horizontal hydraulic conductivities are also given. You are required to determine the rate of flow of water into the trench. Now let us solve this problem step by step. Step 1. Calculate an equivalent hydraulic conductivity using the equation given here. Since the vertical and horizontal permeabilities are known. Step 2. Determine the hydraulic gradient. Initially, we draw datum at the bottom of the trench and reference other quantities to it. Elevation head at the base of trench in this case is 0. So is the pressure head, and therefore the total head at trench is 0. On the other hand, elevation head at the base of canal is the difference between 992 meter minus 991 meter, which is 1 meter. Pressure head at the base of canal is the difference between 1000 minus 992, that is 8 meter. So the total head at canal is 9 meter. Head difference is the difference between the total head at canal and total head at trench, that is 9 meter. In order to calculate average length of flow path, we need to determine the slope of the ground surface, which is 4 degrees, and the average length of flow path in that case is 100.30. We know that hydraulic gradient is the ratio between head loss and the travel distance, which is about 0.045. The final step is to calculate the flow rate. Assume that flow is parallel to the slope and consider a vertical section of the trench. The cross-sectional area in this case is equal to 2 squared meter, and the rate of flow into the trench can be estimated by Darcy's approach, which is equal to 0.41 times 10 to the minus fifth power cubed centimeter per second. That's it. In the laboratory tests, only the permeability of a small volume of soil obtained from a specific location is determined. Moreover, since the samples taken from the field are used, they are unavoidably disturbed by sampling process. For those reasons, there exist doubts about the accuracy of laboratory permeability tests. There are several methods to determine the permeability of soils in the field. Two well-known of them will be explained to you. The first one is the rapid field test. A rapid form seepage test may be conducted in the field on cohesional soils. 2 boreholes or trial pits are dug in a situation where a natural permeability is available between them. A quantity of a quantity of pressure dye, as shown in the figure, is introduced into the up gradient hole, and the time required for it to come out in the other hole is recorded. Then the seepage velocity and the hydraulic gradient will be in the form given here. Remembering Darcy's law and substituting, we get the equation as shown here. Another field permeability test is called pumping test. In performing the test, water is pumped out at a constant rate from the test well that has a perforated casing, and the decrease in groundwater level is measured at observation wells established at various radial distances around the pumping well. Regular observations of the water table in the test well, as well as the observation wells, are made after the start of pumping until steady state condition is obtained. Steady state is set up when the water level in the test well and observation wells becomes constant. Pumping tests can be carried out under unconfined and confined aquifer conditions. In the figure, you see the setup of pumping test for unconfined aquifer condition. In section, you see pumping well and the observation wells located at a radial distance around the pumping well. All wells have perforated casing extending to impervious layer. The aim of these casing is twofold. Firstly, it prevents the collapse of soil into wells. Secondly, it enables water to flow into wells easily. The water level before pumping and after pumping are also shown. Now, when the steady state condition is established, the flow of water is considered through an elemental cylinder as shown in the figure. This cylinder has radius r, thickness dr, and height h. Now let the dh be drop in total head over a distance dr. Then the hydraulic gradient can be defined as a ratio between dh over dr. The area of flow at a radial distance from the center of pumping well can be given as 2 times pi times r times h. Let me explain the concept of area. When the elemental cylinder is split, you will have a rectangular cross-sectional area, the width of which is 2 times pi times r, which is the circumference of elemental cylinder, and h is the height of the cross-sectional area. From the Darcy's law, the flow of water can be calculated as 2 times pi times r times H, which is the area, and times K, which is permeability, and times dH over dR, which is hydraulic gradient. If the above equation is rearranged and integrated between the limits R sub 1, R sub 2, H sub 1, and H sub 2 as shown here, when the integration is completed, we get this equation, which is needed to calculate the coefficient of the permeability coefficient of soil subjected to pumping test under unconfined conditions. During test, the quantities R sub 1, R sub 2, H sub 1, H sub 2, and Q are measured. And then the coefficient of permeability of soil can be calculated from the above equation. This test is only practical for coarse-grained soils. It is important to note that pumping tests lower the groundwater, which then causes stress changes in the soil. And these changes in the soil will not be uniform. Therefore, pumping tests near existing structures can bring about uneven settlements. When a pumping test is planned, this possibility should be kept in mind. As mentioned before, the pumping test can also be conducted under a confined aquifer condition to determine the average coefficient of permeability. Pumping is continued at a uniform rate until a steady state condition is established. Since water can only enter the test well from the aquifer thickness as shown in the figure, notice that the water-bearing strata is confined at the top and at the bottom with impermeable layers. In this case, the steady state of discharge can be written as 2 times pi times r times capital H. This is the only difference between the confined and unconfined aquifer conditions, times K times dH over dr. Now, if we rearrange this equation and integrate between the limits, then we get this equation, which is needed to calculate the average coefficient of permeability for a confined aquifer condition. Practical example 2. A pumping test was carried out in a soil layer of 50-meter thick to determine its hydraulic conductivity for the aim of grouting improvement. The rate of pumping was 10.6 times 10 to the minus third power cubic meter per second. Now, regarding the soil profile and test details given in the figure, determine the permeability coefficient of soil layer. Since the test is carried out under unconfined condition, the related equation should be used, as shown here. Putting the related values in this equation, we get the permeability of soil subjected to pumping test, which is around 5 times 10 to the minus second power centimeter per second. Now it's quiz time. The first question: water flows through soil due to the difference in what? Yes, the answer is C, total heads. Good. The second question: Darcy's law can be expressed as, this is an easy one. Which is your choice? A, yes, hydraulic conductivity times hydraulic gradient. Nice going. The third question: falling head test is suitable for what type of soil? No, that is for coarse-grained soils. So this one is for clay soils. Good. So the answer is C. Well done. Referring to the figure given here, answer the following questions. Question 4. Where do we usually draw the datum line? Yes, it may be A, B, D. Yeah, there are several answers to these questions, but the most preferable one is D, because we draw the datum line at the lowest water level. Question 5. What is the total height at point D? No, it is not. Sorry. No. The answer is C. It is 0 because there is no water flow beyond the soil mass. So you should remember these. And the final question: what is the pressure head at point D? Now you know the total head, and pressure head can be easily figured out. Who said that? Yes, the answer is D, -3. Congratulations. Question 7. Which of the following is incorrect? The permeability of soils depends on what? Come on. No, it is not. It is not. The answer is E, heterogeneity. Final question: which of the following statements is not correct? Be careful. Yeah, which one? B. Yes, the answer is B. Field permeability tests are less reliable than laboratory ones. What is the correct form? Field permeability tests are more reliable than laboratory ones. Well done. Well, that's all I have for today. Thank you for your participation. Have a nice day. Hope to see you again.